Following on from our previous video where we introduced likelihood functions and using these for estimation, I'll now do a problem of estimating the probability of a coin landing heads. For those of you who've never seen me or have never met me off camera, that's exactly what I look like on the right. So let's say that the number of heads on a given flip will be a Bernoulli variable parameter p, because it's either 0 heads or it's 1, and I don't know which. But I do know this has some propensity p towards landing heads, but I want to estimate this p. Well, the way I would do this is I'd actually get a sample, and let's say the number of heads on the first flip was 1, the number of heads on the second flip was 0, because it landed tails, the number of heads on the third flip was 0, because it landed tails, the number of heads on the fourth flip was 1, because it landed heads, and so on. I can use the probability mass function for Bernoulli with parameter p to estimate what I think the p is given this set of observations. Well, what I can say is well, the first coin will have given me 1 heads, which it did, with probability p. The second coin will have given me 0 heads, which it did, with probability 1 minus p. The third gave me 0 with probability 1 minus p, and so on. So if you compare the sample 1, 0, 0, 1, 1, 1, and so on, to the likelihood function p, 1 minus p, 1 minus p, and so on, every time I got a 1, because it landed heads, the likelihood function multiplies by p. Every time I get 0, because it landed tails, the likelihood function multiplies by 1 minus p. So tidying that up a bit, what I get to is I get to a likelihood function, which is p to the 7 multiplied by 1 minus p cubed. Now, in fact, that function probably is one of the rare cases that I could probably differentiate easily and optimize by finding the p, but I won't do it. I'll do the general framework of taking the logarithm of that. So the log of p to the 7 is 7 log p, multiply that by 1 minus p cubed, and its logarithm gets added, which is 3 log of 1 minus p. Now, I haven't justified that differentiating that will give me a maximum rather than a minimum, but it has to be, because clearly I can make that likelihood 0 by pushing p close to 0 or p close to 1. I know p isn't 0 or 1 because I saw both outcomes, heads and tails. If p was 0, I'd have never seen heads, and if p was 1, I'd have only seen heads, and neither of those things happened. So I know that I could make the likelihood function 0 by having a terrible estimate of p being 0 or 1. So it's going to have a turning point, which is a maximum. Now I've plotted both the likelihood function itself and the log likelihood function. They're on the same the same horizontal scale between 0 and 1. The vertical scales are obviously different. But if I differentiate this, I'll differentiate the log likelihood function, differentiate 7 log p, and I'll get 7 over p, differentiate 3 log 1 minus p, and I should get minus 3 over 1 minus p. So I find a turning point by finding where the derivative is 0. So I solve 7 over p minus 3 over 1 minus p is 0. And when I do that, I get that p is 0.7. And so it's telling me that the maximum likelihood estimate here is that p is 0.7. So I call p hat, MLE is 0.7. Now I can sense check that a few ways. Partly, in fact, graphically, that is the maximum. It's a little bit more obvious not on the log scale, where it's sort of more peaked. But on a more simple basis, the coin was flipped 10 times, 7 heads were recorded. So without any more information, my best guess of its likelihood, its propensity to land heads, is 7 out of 10. Also, if I'd done this by the method of moments, matching the first moment, I would have matched and got P is 0.7 because the first sample moment for 10 and P would give me an estimate of 10p, and I'd be left with 10p equals 7, so P is 0.7. So now if I've got a harder case, if I think of a normal distribution with two parameters mu and sigma squared, and let's say I know neither mu nor sigma squared. Still, I can write down the likelihood function, and that's just writing down the product of all of these normal densities evaluated at each xi which I observe. So when I do this, I've got a 1 over root 2 pi at each term, so I've got n of those multiplied together, so I've got root 2 pi to the minus n. I've got 1 on the square root of sigma squared in each term, so I've got that to the minus n. And then when I multiply the exponentials, I just add their exponents. When I take the log likelihood, I note that the log of root of 2 pi to the minus n will give me minus n over 2 log of 2 pi. Similarly, I get minus n over 2 log of sigma squared, and then the log of the exponential just brings the exponent down. If I wish to estimate the parameters, I'd need to work out the turning point differentiating both with respect to mu and with respect to sigma squared. No, not differentiating with respect to sigma, because I'm interested in the variance sigma squared as one parameter. If I differentiate this with respect to the mean mu, then the two terms that are not in the summation don't depend on mu, so they vanish. When I differentiate the term within the summation, I'll just be left with minus the sum of 2 mu minus 2xi divided by 2 sigma squared. And then when I differentiate within, with respect to sigma squared, the first term still vanishes because it's a constant. The second term will give me minus n over 2, now times 1 over sigma squared, and I'll get a similar thing within the summation, but of course, what I'm differentiating with respect to is in the denominator now. If I set both of those to 0, the point at which both of those derivatives are 0 are when I have maximized the function with respect to both parameters. Now, the first of these is quite easy to solve. And when I do that, I will just get, because I'm adding n terms, each of which within the sum are 2 mu, I'll get 2n mu. And then I'll just get minus twice the sum of the x's. The denominator doesn't matter because I can multiply up by it, and I'll be multiplying the right side 0 by it, so it will vanish. So when I rearrange that, I will get my best estimate of mu by maximum likelihood estimation is just the sum of the xi's divided by n. So in other words, my estimate of the population mean is just the sample mean. So this is exactly the same as I would get by the method of moments. To get an estimate of sigma squared is a little bit messier, but again, I can tidy this up. I can multiply everything through by 2 sigma squared to clear up the denominator. And when I do, and I start to tidy this up, and I replace the fact that my mu I would have to estimate with mu hat by MLE. And what you start to notice there is that this is just the second central sample moment, or the equivalent. It's the sum of the squared differences around the estimate of the mean over n. So what this actually is this is exactly the same estimate. So if I used maximum likelihood estimation, or I use the method of moments for a normal distribution, I would estimate the exact same parameter values through 2 totally different methods.